two pictures are the picture generated by AI, and they are presented by these two. On the left-hand side, you have this streaks, which correspond to triangulation and braid group of type C. And I want to tell you a story how to deform the left-hand side picture to the right-hand side, which is like a fox. Is another triangulation, which corresponds to braid group of type D. And also the corresponding category is kind of from type C to type D. Yeah, so that's the outline of the talk. So first I will say something about the arting braid groups, and then I will talk about the corresponding KBL category with the symmetry of this kind of arting braid groups. And then I will talk about model spaces from two points of view. One is stability condition on triangular categories. The other is model space of quadratic differentials. And finally, I will tell you the calculation of some model space in terms of arting braid groups. So first is arting braid groups. So the algebraic definition is very easy, that you start with some thinking diagram of finite or spherical type or Euclidean or affine type. And the associate arting braid group is that for each vertices of the graph, you have a generator. And for a pair of vertices, Bi and Bj, you have a braid relation of order Mij, which correspond to this edge between them and with this multiplication Mij. So the braid group, if it's order 2, is commutative. And if it's order 3, it's kind of the usual ABA equals BAB braid relation. And you can also have higher braid relation like this ABAB equals BABA. And today we will only consider these three types of braid relation. And for example, if you have an A2 quiver, and then the corresponding braid group will be the braid group of 3 strings, which is just generated by 2 generator and satisfy ABA equals BAB. And so the wire group, which is a little bit easier to understand, is that on top of the braid relation, you add on the square to 1 relation, then you get the wire group. So the finite thinking diagram or spherical ones, meaning that the corresponding wire group is finite. And for Euclidean type, yeah, it's affine wire group. So it's clear that, yeah, these two groups have a close relation. And so more precisely that, for example, if you take ADE thinking diagram and you take the corresponding Cartan subalgebra, you can think this as just some complex plane. And say in type A is just C to the n, where n is the rank of the number of vertices of the quiver. And then you can take the regular part of this Cartan subalgebra, which is basically you take out the hyperplane which perpendicular to the root. In particular, in the finite type, this is precisely like that. In the affine type, you also need to take some affine hyperplane, but basically you are taking out some affine certain hyperplanes. And then the wire group acts on this regular part of Cartan subalgebra freely. And we know that the pi1 of this hyperplane arrangement equals the braid group. So from this, you can also see that there's a surjective map from the braid group to the wire group. And moreover, this type of hyperplane arrangements and this kind of space is usually K-pi1, in the sense that the universal cover of this space is contractible. So this is a famous conjecture in geometrical group theory. And And for the finite type, it was proved by Lin many years ago. And 5 years ago, the Euclidean case was proved by Panini and Salvati. So a related conjecture by Kasevich and Zorich is that if you take the multispace of quadratic differential, which we will mention in more details later, they're also very similar to this K-pi1 space, because if you take a polynomial and consider the polynomial as the quadratic differential on CP1, the corresponding multispace can be identified with this type of hyperplane arrangements of type A. So they have also this conjecture saying that this type of multispace is also K-pi1, meaning that its universal cover is contractible. So that's kind of our motivation to study this type of things. So the categorical point of view is that the universal cover of this type of space is given by space of stability condition. So that's the general story. So for braid group, the generator is this braid twist on mapping class group of a surface. So basically on surface, if you have some decorations, you use an arc to connect the decoration, and locally you can twist this. So if you take there's another type of twist called L twist. It's the point pushing diffeomorphism, meaning that you push a decoration along a loop, you get an element in the mapping class group. So these are the topological realization of braid group. So basically, we want to embed the braid group into the symmetry group of some surface. That's kind of the idea. And this picture showing that this type of symmetry, in fact, you can have extra structure on the surface. Basically, this type of foliation structure, which we will mention in more details, that these are the geometrical realization of the generator for braid twist or L twist. So yeah, essentially we will later embed the understand the braid group as the fundamental group of some moduli space, and this type of picture are points of those moduli space. So in particular, let me explain a little bit more about the braid group from triangulations. So here we have a trigon with two puncture. So this P1 and P0, they are punctures. So they are kind of a boundary component of the and this surface, but it's just shrink to a point. And there's another type of things I draw here is the decoration. So later the puncture and the boundary component will be the pole of quadratic differential, but those decorations will be the zero of the quadratic differential. So for this so for this surface with marked point, and you can take the triangulation of this marked surface. So I'm saying the marked surface is like this triangle with two puncture in the middle, and then you can draw other arcs connecting marked points or puncture to divide the surface into triangles. And we require that in each triangle you have a decoration. So this is the kind of points in each triangle. So the green arcs form a triangulation, and the red arc are the dual graph of the triangulation. So for each arc in the dual graph of the triangulation, it will correspond to a vertices in the quiver. So here we have a triangulation T. Here we have some quiver associated to it. Yeah, and if two arcs just intersect at an endpoint, they will connect by an edge in the quiver. Although, I mean, we didn't draw the orientation of the quiver at the moment. And for this type of loop arc, so the endpoint coincide when it intersects another arc, we will connect the corresponding vertices, and we will have extra this label 4. Then here we get a thinking diagram of type C, affine type C. So this is C5 tilde. So then we can do the flip of triangulation like this. So after we do that, the triangulation changes as well as the dual graph. So we will associate another quiver similar to before. The only difference is that every time you have two arcs which intersect in both endpoints, and they enclose this type of puncture, which I change it to a Tai Chi thing, is kind of the Z2 symmetry going on there. Oh, sorry. That means that we will change the singularity type of that puncture. And in that case, for this two arc, we will draw no edge between them. So between eta 4 and eta 5, we will draw nothing. So I mean, if you know the Quill's potential story associated with triangulation from cluster theory, yeah, this is natural. So after we do one flip of triangulation, we get a corresponding diagram from C5 tilde to B5 tilde. And if we do it again, we get D5 tilde. So that's kind of the braid group we will associate to the surface, so that we have a geometrical realization that each generator of the braid group will correspond to like a braid twist we mentioned in the previous, yeah, in here. So for each arc, which the endpoint doesn't intersect, then we will associate with a braid twist for each arc which endpoints coincide. Then we call it a L twist along that arc. Then we want to use this type of symmetry of the surface to realize braid group. Yeah, that's kind of just the combinatorial game at the moment, and I haven't proved anything, but let's see. First, let's see the associate categories. So first, let's recall the construction of Keller. Is that if you give me an algebra, DG algebra A, I can do a N completion of this, which is basically the tensor DG algebra using A and its dualizing complex. So basically, we manually make this DG algebra Calabi-Yau. So from Quiver point of view, it's much easier to see is that you start with some quiver. So the edges of the quiver correspond to x1 between simples for the module category of the associated Jacobi algebra, for example. Then in order to get Calabi-Yau property, we want to double the quiver, so that because each edge between two vertices correspond to x1 between the two simples. And if we double the edge, then we will double the home space. So then we will have x1 between S1 and S2, and then x2 between S2 and S1. So it will be Calabi-Yau 3. So that's kind of the doubling procedure from the quiver point of view. So, and moreover, from the cluster theory, we know that you also could have potential from the data, which is oriented cycle, or the sum of oriented cycle. Actually, this potential should correspond to the some elements in the Hodge homology, but combinatorially, it's just some cycle. So each time you have this cycle, you can add some differential, which basically you should understand this as some relation. So in this example, it's like if we have partial dAj star equals aj plus 1, aj minus 1, it's kind of this should equals to 0, because you kind of have d squared to 0. So Quiver's potential is just a symmetrical way to tell you Calabi-Yau 3 DG algebra, where this relation given by the potential. Yeah. So this is the standard story in representation theory. So the corresponding category we are taking is the finite dimensional category, or nowadays we usually call it perfectly valued derived category. Yeah, so it's generated by the simple DG modules. So the deformation in this slide means that if we start with this 3-cycle quiver, we can do the Cabell completion using 0 potential. But then we can deform the potential, so changing the relation in some sense to get another 3 Cabell category. So deformation here means that we change the elements in the Hodge homology. Oh, sorry. Yeah. And then we will change the category in the sense of Keller, so deform this Cabell category. But combinatorially, we just change the potential term. Yeah, so now back to the story that when we have a surface, so what we mean is, for example, we can have a marked surface like a pentagon, or as before, we have a triangle with 2 marked points in the middle. Then we can take a triangulation of this surface, and then we can naturally associate a quiver's potential such that the quiver correspond, the vertices of the quiver are arcs, and the edges of the quiver are the angles in the triangle. Yeah. So that's kind of the idea of how you associate a quiver. And then for each puncture in the interior, so in the cluster story, we just say that for each puncture, there's an anti-clockwise circle, and you always minus this cycle in the potential. But now what we want to do is that for the puncture, we want to divide it into 2 sets. We will only kind of deform the right moon in the sense that, so here we will add Z2 symmetry. And so, yeah, I will draw things in this yin-yang or Z2 symmetry symbol, meaning that for those type of puncture in the potential, we will divide, we will subtract the cycle around that. So, yeah, this is a slight change from the classical cluster story. And then for this quiver's potential, we can get a 3 Cabell category. So it depends on the choice of this partition of the puncture set. Yeah, so for example, if we have this diagonal with 2 puncture, yeah, we take this triangulation. And then the quiver is always the purple one. So in this quiver, there are 4 triangles. So you have a triangle here, you have a triangle here, you have a triangle here, and a triangle here. So the typical in the cluster story, what we do is that we will take this potential. So you take the sum of the 3 cycle correspond to the triangle, and you minus the 2 3-cycle around the puncture. So that's the non-degenerate quiver's potential you want to associate to a triangulation. However, what we want to do is that we want to consider 3, or in fact 4 cases in this. Yeah, so we will first start with the potential which only consists of triangles correspond to triangles. So 3-cycle in triangulations, the triangles. So that's the one you start with. And the reason for that is the corresponding Jacobi algebra, it is Jacobi infinite. However, it is gentle. So if you consider this one from the class story, it is Jacobi finite, non-degenerated. Yeah, but it's skew gentle in some sense. So this one is gentle. Yeah, it's not It's degenerate, but it's gentle. Yeah. And then we can also just take out one of the term in the potential. So this basically corresponds to this kind of half gentle, half skew gentle, halfway between them. So we want to consider all three cases and all the three Cabell categories associated with these equivalence potentials. Yeah, and basically correspond to the previous story. The first one correspond to type C tilde. The second one is type B tilde, and the third one is type D tilde. Yeah, that's the correspondence we will mention again later. So next, let's talk about the moduli space associated with these three Cabell categories. So the abstract definition is that if you give me any triangulated category, we have the notion of stability condition due to Bridgeland, which consists of two structures. One is this central charge, which is basically a group homomorphism from Grothendieck group to C. And the second data is a T structure, but you want to take R collection of T structure. Although, I mean, there's an equivalent definition that you only take one T structure and you take its heart and together with the central charge, but you need to satisfy certain condition, which essentially tells you that, in fact, you have R collection of T structure. So this, you can just take one copy or you can take R copy, it's equivalent. But the important result Bridgeland proof is that this abstract definition give you a complex manifold from any triangulated category. And this central charge basically is a local coordinate for this complex manifold. So you need to carefully glue them together. But from this talk, I want to kind of more emphasize on the mirror side of this complex manifold, which is the moduli space of quadratic differential. So the first definition for this moduli space is given by some numerical data. So we have a Riemann surface, it has genus G, and you need to give me a bunch of integers. So for each integer I, you give me Wi, and they correspond to prescribed singularities on this Riemann surface. Of course, they need to satisfy certain conditions, but basically for this Wi, it corresponds to the i's singularity. If it's bigger than zero is it's the zero of this quadratic differential, which locally you will have something like that, the coordinates. So it is a section of the cotangent bundle tensor square. So for the -1, you have the pole of the quadratic differential. So as I mentioned before, for example, if you take a polynomial and say the discriminant is non-zero, then you can consider this polynomial is a quadratic differential given by this global form on CP1. So I just write down this section of this cotangent bundle tensor square by this formula. And then, I mean, this polynomial, although usually it's defined on C, but you can use the coordinate change to also have definition on infinity. And on infinity, you see that it's a order n minus n-5 pole. And for this polynomial, because the discriminant is non-zero, then you know it has, say, here an m equals n+1. You have m number of simple zeros. And the first zero meaning that it's a CP1. So a polynomial, you can think of this as a quadratic differential on CP1 given by this form. So another case is that if you take a polynomial, divide a fraction of polynomials, And this also define a quadratic differential on CP1. And you just need to see that the order of the zero and the pole at different places. So for example, at point P1, it has a pole of order 2. So this -2 you have contributed in this order 2 pole. And this P2 also contribute 1. So you have this 2 for this numerical data. So this 2 is W2. The W -2. Yeah. So that's kind of the quadratic differential we want to study. So yeah, basically we will mainly focus on the CP1 case. So basically means that the quadratic differential, you can always write it as fraction of polynomials or just polynomials. Yeah. So the important structure for quadratic differential is that, so yeah, you can just think that locally you have this form. So you have some polynomial, you have dz tensor square, and you can change of coordinate to some dw tensor square. So for example, if you have z dz tensor square, so w will be z 2 to the 3. Yeah, an easy calculation. You can show that this w is in fact given by integral of this square of f. Anyway, so if you use the distinguished coordinate w, then if you solve the imaginary part of w is 0, so if you think that on C, the trivial quadratic differential is this one, and so basically means w is z, then imaginary part of z equals 0 gives you the horizontal foliation on C. So you just take imz equals 0, then the equation tells you the horizontal are the geodesic. And in general, when you have singularity, so on the left-hand side, you have simple 0. This is simple 0, something like that. This is in the middle, you have a regular point or smooth point. And here you have order 1 pole, so something like that. So that's the foliation structure. You solve the imaginary part of w equals 0. That's what you get. So in the middle, it's very complicated. It corresponds to order 2 pole. So for order 2 pole, basically, depending on the residue, the foliation will be very complicated. Yeah. So we will treat them separately. And on the right-hand side, we have high order pole. Yeah, so this is order -3, -4, and -5. So you see that the number of distinguished direction in a singularity is always the order of the singularity +2. Yeah, so for -3, you need to -3 + 2 is -1. You take the absolute value, you see that there's just one distinguished direction. So for the pole, what we will do is that we will do a real blow up, replacing the pole with a boundary component, and the distinguished direction corresponds to a marked point on the boundary component. Yeah, so for this one, order 5 pole, we will replace this pole with a boundary component with 3 marked points. So that's kind of the procedure you do when you have singularity or high order poles. Yeah, you should get boundary components by real blow up. So all the singularity can be translated to a topological data, which is what we call a weighted degraded marked surface with punctures. I mean, the terminology is very long, but it's very natural because for 0 and the simple pole, so basically for the left-hand side, for these 3, and these 3, we want to have decorations. So basically, what we draw a circle in red, and we will tell you the order of that decoration. So that's one type of singularity. And the second one is the puncture, because it corresponds to double pole, because they just behave very differently from everything else. And the third one are the high order pole, which after we do real blow up, it becomes a boundary component with marked points. So as we just showed. So basically, originally when we have a model space of quadratic differential, we say, you tell me a genus, tell me many integer numbers. Now we translate this into a decorated mark surface, say a pentagon. So it has a one boundary component with 5 mark points. Basically, this boundary corresponds to a -7 pole. And maybe you want to tell me that there are 3 simple zeros. So you draw 3 decorations with weight 1. So that's all the data you need to tell me to define a model space of quadratic differential. And this also connects to the previous data that when we want to consider a triangulated category, what we do is that for this data, we associate a triangulation. And for the triangulation, so we can have a quiver potential. So in this case, it's just the A2 quiver. And then you can define a 3-carbonyl category for this quiver. So basically, starting from this topological data, we can define some model space, and we can also define some stability condition from the 3-carbonyl category associated to it. So for the model space of a cubic polynomial with non-zero discriminant, then it corresponds to the pentagon with 3 simple zeros. And for another example, so previously we considered the triangulation of diagon with 2 puncture and 4 decoration. It corresponds to the model space of this type of singularity type. Yeah. So at the moment, each puncture are just puncture. So we haven't deformed them yet. So before we do that, we first say a little bit more about this model space. So usually people consider the model space is that a point in the model space is the equivalent data for any so for any Riemann surface with quadratic differential. So these are the 2 data. So this is Riemann surface. This is quadratic differential. However, we want to add one more data as framing, because we already know that the decorated mark surface with puncture can capture all the singularity type. So when you have a quadratic differential on Riemann surface, we can do a blow up and consider a homomorphism from your initial combinatorial or topological surface to the real blow up of the Riemann surface, such that the decoration corresponds to 0, blah, blah, blah. So everything matches. So this is the framing. And the reason we want to add this framing is that then the mapping class group or the symmetry of the surface will built into the data. And also in this talk, we will only consider the simple 0 case, because we will only consider the triangulations. So that's one of the main restraints for this talk. And in this case, the number of decorations is determined by the other data. So you should be familiar with this story in the sense that when I give you a pentagon, I don't need to tell you how many decorations, because you just take a triangulation. I will put a decoration for each triangle in the triangulation. This is an invariant for the pentagon. So pentagon is the data equivalent to pentagon with 3 zeros, 3 simple zeros. Yeah, so in the story of forming Shapiro and Thurston, they start with a marked surface, maybe with punctures, and they will take the triangulation, blah, blah, blah. They never mention the decoration, because they don't need that data for some sense, in some sense. So in this case, we can use all the symmetry of the this surface with decoration to do the framing, or we can just use the marked surface without this decoration. So the difference between these two are the symmetry difference between if you forget about the decoration or not. So basically, you can either consider the symmetry group for the pentagon with 3 decoration, or you can consider the symmetry of the pentagon. So for the symmetry of the pentagon, it's very easy. It's just a rotation. You have this C5 symmetry. But for the symmetry of the pentagon with 3 decoration, so the difference is this surface braid group. And in this case, it's BR3. So because you have 3 decorations in this disk, you can move them around. That's just the definition for braid group of 3 strings. Yeah, so in general, the definition of surface braid group is the kernel of this map induced by forgetting about the decoration. So now, in the equivalence potential case, we say that if we take a partition of the puncture, we can deform the potential by adding some term or subtract some cycles. So that's the definition in the equivalence potential story, which corresponds to deformation of the 3 carbon category. So what about in the model space? So in the model space, after we take this partition, we want to add the Z2 symmetry for the for this right moon. So for some set of the double pole, and in terms of geometry, we are allowing the collision of simple 0 and the double pole. So basically, in the singularity, each time we have a 1 and a -2, we can combine them to a -1. So that's kind of the idea. So in this case, we start with some model space, and we add more stratum with different singularity type. Let's see some example. So maybe let's go here first. So in this case, we have a diagonal with 2 puncture and 4 decoration. So we start with this model space. So now, if we want to deform P2, in the sense that in the equivalence potential, we want to subtract a triangle around a 3 cycle around P2. And in the model space, what we do is that we want to add another stratum to this stratum. And all the stratum we add, so for the initial stratum is kind of the top stratum in the sense that the dimension of this is bigger than all the others. So you are adding some small dimensional stratum into this top stratum. And the way we do that is that we take out a 1 and we take out a -2 and we form a -1 in the singularity type. So if you want to draw the picture, is that you still have a diagonal, you have a puncture, you have then 3 simple 0, but now you have a -1 pole. So basically, you want to collide a decoration to a puncture. So that's kind of the procedure you do for the model space. And you can do it one more time. And another thing we want to add is that we want to add this Z2 symmetry. We want to add this Z2 symmetry manually in some sense. At this stage, from the point of view of quadratic differential, it's a little bit artificial, but later we will explain why we want to add this Z2 symmetry. Yeah, we have a good reason for that. But anyway, so when you have this kind of topological surface with marked points, with decoration, with puncture, it corresponds to some singularity type, and also you can take a partition of the puncture to form some model space. So that's the deformation from this side. And for the symmetry group, you also need to add on the Z2 symmetry to the symmetry group, as you expected. But let's say the main theorem here is, so you start with some marked surface, maybe with some punctures. And for the set of puncture, you also want to do a partition. So after that, we construct some model space, and you can take out the mapping class group to get the real model space. And on the categorical side, we have some 3-carbon category. And I told you that Bridgeline have this machinery to produce you a complex manifold called the space of stability condition. And you can also take out the symmetry of the category. And then these two sides matches. So this is an isomorphism between complex orbifold. Yeah, so because we have taken out all the symmetry, it's not a manifold, it's orbifold. So originally, if you consider the category from cluster story, then you will have this non-degenerate equivalence potential. And so Bridge and Smith prove this result. So basically, they need to take the all the puncture to be collidable double pole, and then you add the symmetry for each one of the puncture. So that's what they do. And then in a joint work with Merlin Kreis and Fabian Hayden, what we prove is that if we take the potential to be the 3-cycle correspond to triangles in the triangulation. So basically, we are considering a gentle equivalence potential. So the corresponding Jacobi algebra is Jacobi infinite, but gentle. In that case, we have this general type of 3-carbon category, which is a little bit different from Bridge and Smith. And we can also prove the corresponding results. But then the model space in that story is the top stratum I mentioned before. So basically, in this example, what I'm saying is this one corresponds to CHQ's theorem, and this one corresponds to Bridge and Smith. And in the middle is in my new preprint. And what is the point of this type of result is that each time you have some quadratic differential, it's very easy to construct the space of stability condition. And the reason for that is that we draw some foliation on the surface. So it's like this type of foliations. So this foliation kind of tell you the slicing or the T structures of the triangular category. And then we also tell you that the quadratic differential have some period map, which is integrates the quadratic differential. You can have the period map like that. So along some arc connecting the zeros, for example. And an arc corresponding to zeros, say eta, correspond to some spherical objects in the triangular category, and the central charge for that is given by the period of the quadratic differential. So that's kind of the idea. And also, I mean, if you're familiar with the triangular category, you know that the key of T structure or slicing is that you have some atrium filtration. And then the geometric meaning for that is broken geodesic. So the foliation is kind of the straight and non-broken geodesic. But sometimes if you want to connect to zero, you need to go around the corner, go through some other zero, and then it's just broken geodesic. And 2 arcs correspond to 2 factors in the atrial filtration. So yeah, so the point is that there's a dictionary. You can translate all the geometric things to categorical stuff. Yeah. So this is the idea of this this type of theorem, starting from Bridge and Smith, and later also given by Hayden, Kazakov, and Kasevich for topological category. Yeah, so as I mentioned before, so the top strata in that case correspond to this space of stability condition on the 3-carbon category constructed by CHQ. And here is the one from Bridge and Smith, which correspond to the class story. But now we can also have everything in between from the deformation on the model space or the category side. Yeah, so This part is kind of easy in some sense, as long as you know how to prove one result of this type. The others is that once you understand the category, it's not that hard. So finally, let me tell you about the deformation of the fundamental group. So basically, the symmetry on the 3-carbonyl category becomes the fundamental group of the model space of quadratic differential. And this is important because previously people had a hard time to calculate this type of topological data. I mean, people know how to classify connected components of model space of differentials, K differentials. So not just quadratic. They have all sorts of things to describe this kind of things. But for fundamental group, well, at least as far as I know, it is not that easy. But now, together with 3-carbonyl category and everything, we can do this work. So maybe let me first mention the main result is that for this type of model space, we can calculate the fundamental group as the kernel of the Abel-Jacobi map. So here, the Abel-Jacobi map, it has some meaning classically, but for us is that you only looking at the surface braid group, which is generated by, I mean, you are moving the decoration around. So the braid twist or L twist, so you're moving some decoration around. And because you always need to go back to the decoration, so each element of the surface braid group will give you some loop in the surface. And if you take the product of that loop, you get some first homology of the surface. And that is the Abel-Jacobi map. And we're saying that the fundamental group is the kernel of that. So although here, I mean, I didn't explain in more detail that we have do some deformation around some of the puncture, allow the collision of zero and double pole. So we haven't say what does that mean topologically. So topologically, basically, it corresponds to we have this type of L twist, and in this symmetry group, we need to say the L twist square equal to 1. Yeah, so that's kind of where the Z2 symmetry comes from. So although we didn't say that allowed, yeah, but here the way we understand the Z2 symmetry is that for each deformed puncture, we want to have this Z2 symmetry because yeah, we add this L square equal to 1 and produces this symmetry. So although from the point of view of quadratic differential, we say that we add this Z2 symmetry manually, but because we know that it corresponds to some space of stability condition on the 3-carbonyl category, and so that's the motivation. Although, I mean, we will mention another motivation very soon. So let's concentrate in 3 types of things for this result. So basically, affine type CBD. So for the corresponding hyperplane arrangement, you can take the regular part of the Carnot subalgebra, or I can explicitly tell you what type of hyperplane you want to get rid of. So basically here, the affine type C, you are taking out many hyperplanes. For B and D, you want to add something back. But then the fundamental group for this hyperplane arrangement is the Y group. The Y group acts on these hyperplane arrangements, and after you take out the hyperplane arrangements and take the quotient, the pi 1 will be the braid group. So that's the previous result we mentioned. And for this explicit hyperplane arrangement, we can write down explicit map to identify, say, for affine type C, they correspond to this configuration space on C01, meaning that on C we take out the 0 and 1, and then we take n decoration. So this is basically the previous picture that we have two puncture, which is 0 and 1, and we want to have many configuration, which are the points, which are in previous notation are the decorations. Yeah, so when we start, we have this picture like a streaks. So this is a triangulation. We take the dual graph, and now we know all the meaning of this picture is that on the outside, this triangle corresponds to this -5 pole, and we have two puncture P0 and P1 correspond to correspond to double pole, and we have 5 zeros. So that's the quadratic differential we have. And then we say, okay, we have the corresponding diagram of affine type C5. So each of which correspond to some elements in the mapping class group. So the theorem here is for the quadratic differential in affine type C, we can always write down it explicitly as kind of a polynomial divided by z square and z minus 1 square. So that's correspond to the double pole at 0 and the double pole at 1. And at infinity, it also have this pole of higher order. And then the model space is more or less the configuration space. And you can calculate the pi1 of this configuration space. And in this case, it is the braid group of type affine type C. So everything matches. And now we want to do some deformation. So as we mentioned before, combinatorially, you can do a flip of triangulation. You change the corresponding quiver and change the corresponding category, and then the space of stability condition, and then we get the corresponding model space, which is the previous model space adding some stratum. So here, what we mean is that we can allow the configuration or the zeros to collide with this double pole at 1. And then what we get is a hyperplane arrangement of type B, and then we know the pi1 of this model space correspond to arcing braid group of type B and tilde. So that's the from type C to B. And if we do one more time to allow this puncture is also collidable, then we change the quiver to type D tilde, and then the corresponding model space of quadratic differential will have fundamental group equals to braid group of type D and tilde. Yeah, so everything matches. So let me summarize the results in this form. Is that if you give me any non-exceptional finite or Euclidean thinking diagram, yeah, so it should be spherical or Euclidean thinking diagram, and then I can find you a surface with marked point, with decoration, with puncture, and I was also need to tell you the partition of the puncture, but then we can find a moduli space realizing the hyperplane arrangement so that the fundamental group realize the arcing braid group of the corresponding type. And in fact, for finite type, so type A, B, C, D, or type A tilde and C tilde. So in all these types, which there's a terminology called the lattice type, we can show that the contractible universal cover for this hyperplane arrangement or this moduli space is given by the corresponding space of stability condition of associate 3-carbonyl category. So the only missing parts are Bn tilde and the Dn tilde, because in these two type, the corresponding 3-carbonyl category is a little bit tricky to understand. Yeah, but for everything else, we can have that. So on these slides, we are specialized to affine or finite thinking diagrams, so basically A, B, C, D, or its tilde. But in general, if we consider homogeneous surface with many poles and many punctures, then we also have the corresponding result of calculating pi 1. And that should you should think of that result as a generalization of affine or finite Artin braid group. So finally, let's tell you the story is that we want to compare this from type C to type B to type D. So basically, for type C, you have this column where the model space is very natural because it is a single stratum for the model space of quadratic differential. And from representation point of view, it is gentle, although usually it's infinite dimensional, the Jacobi algebra I'm talking about. And it's also very nice because in the joint work with Moni and Fabian is that we can have a Professor Schobers to describe the whole category. So we can understand more or less everything about this category, 3-carbon category. And a recent work by Williams and his collaborator, they say that the DT environment for this 3-carbon category is also natural from the point of view of mass physics. So yeah, somehow this CHQ is kind of the generalization of affine type C. This category is gentle, which is everything is very nice. So on the other side, on the other hand side, so the story of Bridge and Smith, they did this work many years ago, and it is also natural from quiver representation point of view because it's skew gentle, it's finite dimensional, the quiver's potential is non-degenerate. So that's why this case is actually easier from cluster point of view. However, it is not natural from model space of quadratic differential point of view. And in Bridge and Smith, they also calculated the DT invariant, but somehow I'm not sure if it's natural or not. Anyway, for this work, from the point of view of hyperplane arrangements, we see that all the things are natural because they are just they have natural generalization of hyperplane arrangements of affine type CBD. So that's kind of our point of view. Yeah, so let me summarize that we have many deformation of things. So basically the Artin braid groups, the categories, the model spaces, and topologically we're taking the fundamental group. So all the things can be matched together. And yeah, that's the punchline of my talk. Yeah, thank you.
So thank you very much for your very nice talk. Are there any questions or comments? I have just one last question. If in your talk you start with the quadratic differentials, and then we have a triangulation, and after that we have a quiver.
Yes.
And you speak about the modular space of these quadratic differentials. On the other right, when we have a quiver, then we have a quiver variety for dimension vector, and then again we have a modular space defined by Aristotle-King. Is there some?
Yeah, that model space is not the model space we consider because it does not correspond to the model space we start with. You need to take the space of stability condition on the triangular category, then you can get the model space of quadratic differential.
Yes. So there is no connection between these two modular space.
if you take some dimension vector, you can take the moduli of the stable object that correspond to that. Then you get this, how to say that? It's just a moduli of some stable, but that's correspond to you are fixing quadratic differential. So that will correspond to some arcs configurations on the Riemann surface. So for example, in the Kronecker case, if the dimension 1, 1 will correspond to a family of P1 family of stable objects in the tube. So that's kind of the things. If you choose some dimensional vector, it's possible correspond to this curve or some ring domain in the fixed quadratic differential with fixed foliation. So I think that's the thing you are talking about, but not the you are not varying the quadratic differential. You are fixing a quadratic differential or stability condition. Yeah. Hello. Oh, it seems the host is offline, maybe. Hello. Anyone know what's going on? Hi, you were
Hello,
offline.
sorry, there is some problem for my connection.
Yeah, no problem. So do you guys have more questions?
I don't understand your answer. Can you?
Yeah. So the point is that when you want to fix the dimension and take the model of the stable object there, that's fixing a stability condition. So in my model space, a stability condition is just a point of my model space. So fix quadratic differential. Then you have some formation structure on the surface, and your moduli, say on the connect quiver case, if you have this dimension 1, 1 for connect quiver, it may correspond to a P1 family of stable object in the tube that correspond to this circle on the surface, which in terms of quadratic differential, it's a ring domain. Yeah, so that's kind of the topological meaning. And in DT theory, for example, for Donaldson-Thompson theory, sometimes they want to count the number of ring domain or set of connection. Yeah, this type of things. Yeah.
Oh, thank you. And the other question is that in your theorems, at least in the example, says that, for example, if you mutate on a triangulation, then the corresponding fundamental groups will change.
Yes,
Maybe it is defined in new mutation on fundamental groups in some sense?
No, because when we do the flip, we modify the singularity here. So the space is that we add some extra stratum to the space so that we kill some loops in the space. So that's why the model space, the fundamental group change from say type C to type B to type D. Yeah, because kill some loops. Yeah, that's the idea. Yeah.
Thank you very much. And are there any questions? Or so if not the case, thanks again. Thank you very much for your very nice talk.
Thank you. Thank you. Yeah, hope you see you in person around at some conference.
Yes, also me. Maybe in Isfahan, if you like, you can visit our institute in Isfahan. We have a small groups on representation theory.
Okay. Yeah, I missed the opportunity. I think a couple years ago there's a conference.
Yeah. There was a big
maybe next time. Yeah, maybe next time.
Yes.
Okay.
Thank you very much and see you.
Bye.
Bye.